Okay, so we're doing section 2, and I'm going to walk us through what should be familiar already from last week, which is actually a pretty busy screen if we look at RStudio here, and this is what I'm sharing. What I want to do, though, is I want to clear the RStudio and get us a feel for what essentially what our working space, our environment looks like when we don't have anything. So I'm going to clear the console, actually, and I'm going to remove this script here. And you'll see that what I have is I'm going to go to the tab, I'm going to do File, and I'm going to open File. And it'll take me to my desktop where you can see right here, what I have saved in the desktop folder is actually, you'll have a couple files like an RData file or an RHistory file that might be blank. Ignore those. What you want is you want to download the popular kids data file, and you want to have the problem set code. And we get both of those from the website. And if I can get us to the website, oh look, I'm trying to open the URL here. That's not what we wanted to do. What I have there is I was trying to open it through RStudio, but on the desktop we actually I have saved in the same folder the location on the website where we can actually download the problem set. So let's see if I can share that web page. We'll see if we can. Looks like I can, more or less. It's taking a while to load, so I'm going to try to load it in Google Chrome, which seems to be faster for me, so we'll try this. Okay. And this is for problem set number 2. So I'm going to move from, let's see, here we have our, well, it's taking too long for me to download from the website. That's fine. Let's see if I can get us to the assignments here. I want to share this, because I think it's important to move from the assignments to getting and loading your data to the web page. So I'll do a screen share of what the problem set number 2 page looks like. Okay, let's preview this. Mine will look slightly different, and I'm going to do a new share of the problem set 2 and where we locate. Well, it's loading. Let me stop the share. I need to share my other web browser. Hold on for a second. I'm going to share Google Chrome. See if we can share this and see what we see. Nope, this is Firefox again. I'm sorry. I should get Google Chrome. Let's try that. Okay, here we are. So here's the problem set we have for this week. And the point here is, of course, we're actually analyzing a different data set, and we do this each week. And this one we're looking at one that looks at psychometrics. Psychometrics is a study of psychology using quantitative measures. And we're looking actually at kids' popularity. And we're going to see why this is numerical data as opposed to categorical data as we progress this week. But the first thing I want to show and review is how to download the actual data set, or as we say in R speak, the data frame. Go here, and you just, I click once on my web browser, and you can see the popular kids data frame right there. And then you click the R code data frame right here. And these are the answer 5 of the 18 questions here. So we get 5 problems here. And these questions I'll review as we go along in the actual syntax here. And you'll see that in contrast, I think, to earlier weeks, some of these are actually write-in answers. Make sure that you round those to 2 decimal places when you can. If not, we do sort of account for differences in answers due to rounding. But that's where you get the data set, I just want to say. And from there, you simply do this. You really want to, ideally, I'm going to share my desktop and minimize the screens. Ideally, you want to have what I have right here, which is problem set 2, saved in one folder. And then you have, if you just, I'll even open up this web browser here, or the window here. You'll see that you should have the R syntax and then, so the R data file and the R syntax saved here. As you see, I saved the sort of a copy of the web page here in HTML code. That's not necessary. We just want these 2 things right here. In fact, I'll even put this in the trash here. The point is that I consider this a type of data hygiene. What we want to do is we want to save our analyses and our data in the same place just for organization. I've looked at other students' homework assignments and their analyses before, and they sometimes don't know where they are working. So the first goal of a data analysis is to, in essence, keep your room tidy, keep your place clean, keep your analyses clean, know what you're dealing with. Because it's very easy to, say, analyze a file in one directory, on one location on your computer, and then go to a different directory. And we don't want to do that. We want to actually keep all of our analyses in the same place for now. You could have more complex analyses where you move from one location of your computer to another, where you download data from the internet. And for the final project, you can even, as I said before, and as we saw with the Titanic data, you can actually download data from R itself. And that actually grabs the data saved to your to a location on your computer as well, or online, depending on the question at hand. For now, we're kind of keeping everything. I would encourage you to keep everything in a nice, tidy sandbox. Think of this as a playpen for now, just to have fun and to really explore what we want to focus on, which are the statistical concepts and the kinds of analyses we do with numerical data. So first, let's take a look at the data file. So I'm gonna switch to RStudio. And I'm going to, let's see, do I have RStudio open? Yeah, we do. I'll share the screen again. And you'll see that the console's empty, but if you see in a very light gray color here, if I can annotate this, you'll see you have what is called, and some programmers might call this, what is that, path file. It's just the location of our analyses. You'll see that I have a certain amount of junk here, but you'll see that I have the desktop, and then I have a folder labeled pset2. That's where all of my analyses are at the moment. That's why sometimes R will create a history file. It'll create sometimes a project file here. Those are sometimes automated. You'll see it actually right here. I'm going to clear all the drawing, and we'll go back to annotation. You can see actually, come on. You can see actually if you look at the files within this particular path file, you'll see that there is the data file. That seems to be a blank one. We don't have to worry about that. We can delete that. Yeah, sure. And then there's this history file, and that will regenerate as you do new analyses. You'll see that they have today's date a couple hours ago when I actually uploaded the data, or about an hour ago. But what you really want is you want the R data frame, and you want the code here. And this is what we download. We drag and drop into our folder. So it's pretty simple. There's not really, I think, much to be confused about right here. And you can see up here, you see the components of the path file, as we call it, the location on your computer. It'll differ depending on a Mac or not. If you press this button, you'll go up a level. You can go back to pset2. But if we go up a level like this, you'll see that we're looking at my desktop, and we see some other files here. We want to go to pset2, and here we have the R code. And if you just click on that R code link once, look, it's another way to open the script. If you recall, last week we used the drop-down menu, File, Open File, and we can navigate to the script right here. It's the same way. But here I'm showing you you can just go to the Files tab on one of your panes, and you can open it this way. And you can click Open the R data file and ask, are you sure you want to open this? And it'll give you the location. Now look at this. R is very helpful here because it gives us what is called like the full path file. In other words, the complete location of the data frame. So here we see the desktop, and it's problem set 2, and it's the data frame popular kids. And that's all in quotes. So it gives us the exact location on our computer for our analyses. I want to move us up to the script though, because what I did is I changed a little bit of the analyses, which is, well, actually you'll see that on line 17, you'll see some commands that I put in here before that we should probably break out just for simplicity's sake. What I'm doing actually here is I'm nesting these commands, or functions rather, but let's define these separately. And then this goes back to our issue about data hygiene. So the first thing we do as before is, remember, we have to install. If you haven't already installed Mosaic, go ahead and do this. I highlight the syntax, or highlight the amount of syntax here, and then you just press run, or you can do the Control-Enter shortcut. And you'll see in the console pane, you'll see that syntax run. And it'll take a little while. You have to be, of course, connected to the internet. And you'll see that says it downloaded some of these packages. Now the next step you have to do, you always have to do this when you run R code, is you have to, in fact, even if you don't install the package, remember you always have to load the package in your working session. In other words, you have to tell R, yes, I want to actually use this package right at the moment. So we're attaching it. So it's another way of calling this function. I believe you can even use the word attach. So we can even say attach Mosaic. And we can also use the verb require. These are all actually the same function. I haven't used attach in a while. Okay, so you don't use attach. You can detach. You can do something else, but you can also use this function require, which is just redundant. Nothing happened here because we already have this in our library. Now, how do we know this is in our library? Well, we can go to packages here and just type in the little upper right-hand corner of the packages tab, Mosaic, and look, we'll have it highlighted. Well, it looks like I actually have, for some reason, I have 2 of these tabs opened up. I wonder if that's because I accidentally typed this command before, or I installed it twice. Let's get rid of this at least. I'm not sure what happened. Well, this is kind of interesting. For some reason, I have Mosaic installed here twice. I'm not sure why. But the important point is, by clicking and declicking these boxes, as we've seen before, you can actually use this library function interactively. And this is what I showed last week. Now, if you just type in this function right here on line 14, library Mosaic, the Mosaic data are already loaded. Again, these are just, it's not required, but these are just data sets that are loaded as part of R that are used for the help files. And there are some examples there. And you'll see that the script here is a little more complex than it was when I just type in the library Mosaic function, but it's just a different way to install the packages. Now, again, you should probably just see one Mosaic package name and then a Mosaic data set package. Again, I'm not sure why I have 2 of these types of packages, but it shouldn't really matter for anything of consequence. If I look at the script here, it looks like I might have one that's slightly updated for version 3.3.1 as opposed to 3.3. That's my guess, but I'm not exactly sure. Let's see if we can remove this one. Well, yeah, looks like this top one is I don't know, it's a little bit older. This is not pretty inconsequential, as you'll see. As long as you can run your script. I was going to type in something else called version. Let's see. No. Well, anyway, let's not focus too much on the packages because we've done that last week. What I want to focus on is this thing called the working directory. This is what the WD is short for. If you've ever used some, I don't know, any scripting languages, you might say Linux or anything else, or Shell, or if you just do a lot of programming in general, you'll work with what are called path files or working directories. Sometimes it's called a present working directory, sometimes it's called a current working directory, it's a working directory. All of this refers to is where you are on your computer. And I emphasized this path file before, which is typically on since I'm working on a PC, personal computer, you'll see it's typically demarcated as a C : users, some username, something, desktop, something. And then what we have on our desktop is a folder named pset2. And this is usually separated by single quotation marks. This is often what's referred to as a path file. There's also something called a relative path file, which would be, say, if you just wanted to change a relative location. What I want to point out is that you can use these functions, 2 functions that are pretty useful. Now, you can actually do this manually by, if we go through our history, actually, where I load the function, if you go to the upper right-hand corner, you go to the history tab, and I did load this package. So I remember I did this load command, and I loaded this data frame. I can actually copy everything until the problem set location, and I can do the set working directory function. And all that means is that I'm telling the computer, every time I run this analysis, I'm going to set my working directory. I'm going to tell the computer, this is where I want to do my analyses. So that's what the set working directory function does. And you can do that simply by when you load the function. You can do this. You can do this by navigating through your windows and copying and pasting the location. And as I said before, this is a PC as opposed to a Macintosh computer. Macintosh computer will use different slashes, and it will usually I think it starts off with just this kind of backslash or maybe a tilde or something like this. I can't exactly remember, but the main point is that the essential element is the same, so we can set the working directory, and all this means is that we just told the computer every time we run this analysis, and we're going to save this script. And we, in fact, I did Control S once I changed it. Once we do this, then we have the directory. In fact, this is where we get the sort of allied function, the related function, get working directory. This tells us where we are. And you can see that this prints back for us. So sometimes you can actually nest these functions. This is called nesting a function, where you have a set working directory, and you can say, I want to set my working directory to whatever it is I'm getting as my working directory. Well, I'm kind of moving away from that. Sorry. Okay, I want to actually highlight this. I don't want to do that all the time because you don't always know what your working directory is. So what I would encourage you to do is actually unnest these and just make sure, confirm first that the working directory that you're using is the one that you'd like to use. So remember, get working directory. This tells us where we are, and then set working directory. This lets us tell computer where to work. And the goal is, of course, keep all analyses and data in the same place. Now, this might seem a little tedious. Why am I spending so much time on this? Well, it's simply because it's quite important to do this, because what I've done now is once I've set the working directory to this location on my desktop, and of course it can be anywhere. I encourage the desktop because it's relatively easy to find. Of course, I also encourage relatively short file names. If you notice, everything on my quote-unquote path file doesn't have any spaces. And the reason we don't want to always have spaces is, let's say, imagine I have one space for the word pset here. Well, sometimes it's hard to tell visually between one space or two spaces. It just creates more difficulty. In fact, spaces are somewhat difficult to define. From a programming standpoint, it's hard to see. What I mean by it's hard to define is sometimes there are things called trailing spaces. I find it to be problematic. And usually you just want to have a path file without any spaces, simply because you're going to be able to define exactly where you're finding things. And also keep it relatively short, because there's already a bunch of syntax. If I wanted to type out my folder, I could actually make a directory or make a folder called problem set2 and spell it out. But you notice I'm already creating a problem here. I misspelled set. It's because when you have that enough text, you're introducing the likelihood for error. And I'm trying to get us moving away from that, actually, and just focus on shorter terms and actually just keeping things as simple as possible. That's a few of my bits of advice, I guess, my platform. What I want to also show is that once you set your working directory, then you no longer have to do this fold command that we did before. I'm pressing the up arrow to go through our previous commands. That's one thing to do if you want to go through your history. You can go through your history file. You saw this command here. You can also just press the up arrow just to go through what you've done before. Now, again, this is on a PC. It might be different on a Mac. But I want to show that when you load, well, I can't even show this, but if you use the load function to load your data set, but we don't even see that here. That's fine. I'm going to reload the file here. Oops, I didn't want to do that. I want to actually, yeah. If we do this load function, just notice it has a lot of text here, right? And again, I said I don't want to do too much text. Well, the nice thing is once you set the working directory, then you can basically load just the data frame itself. And notice again, you have the name of the data file in quotes. You have everything that is in capitalized to be in caps, and then you have this type of file. there are a few kind of R data files that we want to be aware of. The most important one is an R data file. And remember that you have a capital R and a capital D to define what an R data file is. And, you know, I talked about some other files like an R history file, but mostly we want to just focus on the fact that we have an R data file and an R code here. So now we can load this R data file. And I want to show that we can load this. In fact, I'm going to delete it from, oh, sorry, I don't want to actually delete it, do I? No, I don't want to delete it from our location. In fact, don't do that. But I want to actually see if it's in our environment. So keep in mind that having a data file in your path file is different than having it in your global environment. Remember, R is an object-oriented programming language. All that's fancy talk for really saying you have an area or a space where you do things, you load and define elements or objects, we call them objects, in that environment. And here we have a data frame as a type of an object. Well, to remove that object, we can actually, if you notice, if you highlight or scroll over on top of some of these icons, you can remove an object here. And I want to show you what the console will show, which should be the syntax to actually remove an object. And you'll see this includes hidden objects. Okay, well, we weren't able to do that this time. But the point is that if you want to clear an object, the easiest way to do it is just to use this little broom. You can also do, I think you can also do everything you can do, by the way, through the interactive menu. You can also do through the console. I think you use it through the remove function. But for now, let's focus on the fact that we can use it through the console. And keep in mind, that's different than, say, deleting the actual file. All we're doing is we want to tell R, okay, I want to load this into working memory. Let's see if I can get this right now. Now we have the data frame in memory, and it is an object. And how do we know that's an object? Well, it's listed here in our global environment. I'm going to show you another command, actually. You actually do this ls command, which actually lists the objects within your environment. And you'll notice that the reason I call R an object-oriented environment is simply because if you notice here in the environment, Popular Kids doesn't have the suffix anymore. It's no longer considered an R data file here, although it is, because it's a very particular type of object. The point is that it's now something you can manipulate. And so basically, the main point I want to go back to, though, is that when you load a data file, you want to make sure that you can place your script as well as your analyses in the same location. And you want to, two ways to take advantage of that are to use the get working directory function and the set working directory function. And those tell us, and I introduced the concept of working directory for those of you who aren't very familiar with that concept. And all that tells us is that establishes where we do our analyses. Then we can use this load function instead of our drop-down menu to load the data frame into our working environment. Now, whenever you change the code, the syntax, the script, keep in mind that RStudio kind of reminds us that we want to save it. How do we know? Well, here we see that the script is actually highlighted in red. There's an asterisk here. So we want to make sure we save this periodically. We can do this, but you can also do the shortcut. And you'll notice that whenever I'm doing analyses, I actually almost do this automatically. It's become second nature to press Control S every once in a while, just to save things as you go along. What you don't want to do is change a bunch of stuff and then forget that. So that's why, for me, it's almost second nature to do press Control S or to use the keyboard shortcut. So here we are. Basically, this is the place where I want you to be, as is the case typically, is I want you to have in your location, in your working environment, your data frame. I would like you to have your problem set syntax in your code to be in one location, typically your path file. And for now, as you get acquainted with R, I want you to use the working directory functions to define where you do your analyses. So that way you can actually include in your script a command to load your data rather than using the drop-down menu. And the reason we want to have a script here and we want to save this is that then I can run and rerun these analyses over and over again. So here I'll rerun again. It'll ask me to restart R. You'll see that I'm just going to do everything I've done before without any hands, basically. I'm reinstalling the Mosaic package. I'm attaching it as a library. I'm defining the current working path file where I'm going to do my analyses, and then I'm going to load the data frame back into R and overwrite the other one. So basically overrode what I've done before. And I do that by highlighting that script and then pressing the keyboard shortcut Control D. And that's the utility of using syntax. So let's go through some of this code. Let's see, we have about a half hour left, but I think we can get through most of this, if not all of it. Keep in mind that when we talk about R, we're gonna see something quite familiar with the R functions, which is that what we do first is we use what they consider, or what they define as an equation style type of scripting or coding, which is simply to say we almost always have some function here, some command, right? Some function, something we want R to do. Then we have a little tilde. I press this shift, and then I press a button on my keyboard that is right below the escape key. And typically I'll put a space there. And then we have the variables. So here we might have the variable looks, and then you have what are called arguments separated by commas. So we have a function, we have a tilde, typically we have a variable name, and I'll just press space there. And then we have data, then we have the definition of the data that we want to analyze. And of course we have the data frame popular kids, and that's case sensitive. And then we close our argument or function with close parentheses. Now, I want to show something to you because you'll see that RStudio is helpful in so many ways. It's telling us right now, for example, that there are a lot of problems with what I've just written. In fact, because we're using Mosaic, and because function is a general term, you'll see that R is trying to understand what I'm doing, it's trying to interpret it, but it takes things quite literally. So what it's doing here is, let's see if I can try fake data, let's see if I can type this. No, okay, so it doesn't care about the fact that popular kids is or is not the data in the data frame. But you'll see that there are these little red things here. And these are good warning signs if you're committing an error. In fact, it's complaining quite a bit. It's complaining about this opening bracket. See, there's an underline there. And it's complaining about this tilde. And you'll see, first of all, that you'll also see that for lines 40 and 41, you'll see that there are problems here. It's saying that there's an unmatched opening bracket. Well, in fact, that's not true. So why is it complaining? We'll see here. It says there is an unexpected token. That basically means there's an unexpected character there. The main point is sometimes R won't exactly tell you what's wrong. It doesn't know, for example, that there is a matched bracket here. In fact, as you highlight the first bracket, you'll see that the line 43 is highlighted. So what it's really just saying is, I don't know what to make of this. In fact, it's because this function doesn't exist that R is complaining. If we take anything and we take the variable looks, you'll see that we'll still see that R is complaining. But if we go to this function mean, and I press escape because I actually don't want to finish typing this out, you'll see it's still complaining. Okay. So that was okay. So this is actually quite helpful. You'll see sometimes R actually makes additional comments on your code. So not only was my function imaginary, but it also didn't like the fact that I had some extra spaces there after the opening brackets. I think it's because I had a space here. No, actually, no, never mind. It's because that function did not exist. So R will sometimes complain, but it won't exactly be as informative as you like. The main point is if those messages do arise, you know something's wrong. And this is where I encourage you, this is okay to do, copy and follow the examples from the text, or in this case, from the script that we provide for you. Now, if you notice, I put everything on every line. And also, if you look at the script that we have in the class, I don't typically put spaces between some of these little characters here. Again, I do that because I think it's a little bit easier to read. And there are a couple functions we're going to focus on. The first one is, first you look at measures of central tendency. And we're going to look at the mean function. We're going to look at the median function. And we're going to look at, well, that's it for now. So the point here is that the mean and the median function, if you look at the question here, and I'm going to open this syntax, sorry, open the pane so that we can actually see all the syntax. You'll see that the first question here asked, based on the average, which of the 4 qualities, looks, grades, sports, or money, did children believe would make them most popular? What is the average for each quality? Remember that each child, rather, this is a typo, each child was asked to rank each quality from 1 to 4, where 1 is the most important quality and 4 is the least important quality. So the point here is that when children are asked to rank things from most to least important, we're creating a numerical set of variables, because each quality, looks, grades, sports, or money, is assigned only one of those values. So imagine you took this yourself. You're asked, well, what's most important for you? Do you value grades, looks, grades, sports, or money? So this is why we do an average of these categories, because for each child, and we'll see this when we explore the data set a little bit more, you'll see that for each child, again, only one value is assigned. So we can do the mean here, and this is just, why does that not work? Oh, interesting. Well, let me make sure I didn't change the code too much. Hold on for a second. And we have the data frame loaded in, so. Okay, so this should work. Let's see why that wouldn't work. Okay, interesting. So for some reason, my function isn't working. And the weird thing is this was actually working before. So let's see why this might not work. Well, one thing to do is, let's say if you have an issue like this, it looks like it's not reading in the data correctly, in fact. One thing to do is to confirm that your data are actually loaded here. And remember, if you click this little tab here, you can actually see these analyses. And it actually looks like everything's working okay. You'll have the variable looks, which is a number, and you have the data frame popular kids. So the question here would be, why does the syntax not work? Well, the easiest thing to do is actually just load your packages again, and just run up to that syntax. So again, this is another example of the virtue of saving what it is you do, because you can simply rerun your analyses if you run into one of these issues. I'll be honest, when I last ran the code, I didn't do this before, but maybe this is related to the fact that I had 2 packages. No. So, okay, this is one of the mysteries of programming. You'll notice that I was encountering an issue before, not exactly sure what the reason was. And here you can see I actually am able to estimate the mean of each of these variables. In fact, I know I'm able to do it for the rest of the variables, because there you are. So what this means, of course, when we interpret the values of this, is it's the average of the children in the data set, where each quality is ranked from 1 to 4. So on average, children will rank looks around 2. So it's about the second most important thing that they're gonna rank. On average, they're gonna give grades a ranking of 2.6. So they're gonna rank it a little bit lower than looks on average. Again, I keep saying on average. Sports, they're also going to put around second most popular. And then finally, you're going to see that children on average are ranking the least important money. And they're ranking that at about an average of 3. So what this gives you is a measure of central tendency, that on average, I keep emphasizing this, most of these are values, most of these traits are giving us, they're giving a score of 2, maybe 3, close to the middle of the distribution. They're not ranking them as most or least extreme. That makes sense because it is a measure of central tendency. So there'll be some, most students will be perhaps coupled around the mean there. This is where we get to the median, where the median is different than the mean, in fact. Now, what is the median? Well, the median is typically a more robust measure of central tendency. And the median, instead of averaging the observations and dividing by the number of observations, right? So we just average everything up and divide it by the number of observations. What we're doing with the median is we're looking at the middle value. And in this case, because there are only 4 values that can be taken on, the median is the average of the 2 middle values. But that's beside the point. The main point is that the median is a more robust measure of central tendency because it actually takes the middle value. Whereas the mean is the average value. So mean, average, median is the middle. And you can see that everything is essentially the same, except look at the syntax here, or the output rather. The median is typically an actual number, because as a middle value, it actually exists in the data set. So it is actually the value that it is in the middle in the data set, as opposed to the average, which is constructed from adding everything up and then dividing by the number of observations. Here, or scaling it to the number of observations. Here we see that the median is pretty close to the mean, in fact. So, for example, if we look at, and the reason that's important, so if we look at, for instance, the ranking of money, we see that it has an average of 3.2 or so, and then we look at the median, that is an average of, or that has a value, a median of 3. The main point is that when the mean is not so far from the median, we know that the measure of central tendency is pretty robust to outliers. That it's not an artifact, the mean or the average is not an artifact of a few extreme values. So an example of where the mean and the median differ is in household income. You have some very, very rich people who are going to skew that distribution so that your mean, when you apply the mean function to a numeric variable, it's going to be very different than the median or the middle value. So that's just a pretty clear example there. I'm going to just scroll ahead. I want to get us to, I think in the last 15 minutes, to line 75, where we take, we look at the head and the tail function. And ideally to this concept here, where we're introduced again this idea of the assignment operator to create subsamples. And I'm going to describe basically exploring the data set in rows to illustrate this key concept this week, which I think is sometimes counterintuitive, which is that even though we're talking about different qualities for children, these are actually numerical variables, and it's because they can be counted. They're not say quality ratings. They're actual rankings that you can place in order. In the same way you can rank height, for example, the height of students. So I want to give us use the extra lines of code just to give an idea of other ways to explore the data set so you can get a better, more intuitive view of it. And then we'll next week, or sorry, tomorrow, we'll go through these more complex analyses where we look at measures of spread, and we'll look at some of these graphs that we see in the plots pane. So just to give you an idea of where we're going to go, we're going to probably end up around line 83. So we have measures of central tendency. Now we have 2 measures of spread. Well, what do we have? Well, fortunately, RStudio makes it relatively easy. Again, it's the same syntax. So here the functions are also easy to remember. SD, lowercase sd, stands for standard deviation. Variance, VAR is the variance function. Now here we're looking at a different variable. We're looking at the variable age. And the question is here looks at what is the variance of students' age? Round the answer to 2 decimal places. Well, this is quite easy if you run the syntax on line 54 here. You'll see that the outcome is this right here. Now, one thing we can do is we can actually also round our analyses to a particular value. Well, we could do that with an R, and I'll show you how to use R for sort of a fancy calculator later. But the point is, if we look at the relationship between standard deviation and variance, we'll see that the variance is a little bit different. That the variance function gives us the actual answer. And again, read this like an equation if you can. And here, I should say, I'll have a little bit of an aside here. We have the time to do it. The equal sign here is as a single equal sign. When it's placed within 2 open and closed parentheses, you're basically assigning something to another value. In other words, here you're assigning your data frame to the data set popular kids. So you're saying, whatever the data set is, I know we have the variable age in the data set popular kids. And here the equal sign is, think of it as an assignment. You're basically, you're basically telling the computer what to do. And I like to, parse code into different lines, if you notice, and put spaces between them. Simply because when you have opening and closed brackets on different lines, then it's easier to read. And you get the same answer here. And if you look at the console, you'll actually see that when you place the code in different lines, the console reads a little bit differently. Anything that's blue is the actual syntax, typically if you're using the default settings. And then everything in black is what's being printed out. And you'll see that if I type everything on one line, say if I do the standard deviation, you'll just see this little, I guess, greater than symbol right here that I have highlighted. And then you'll have the output. But if I move the syntax to multiple lines, you'll actually see a plus sign for every line until the argument is finished, and that's with the closed bracket. So in the console, the output is read a little bit differently. Now keep in mind the relationship between standard deviation and variance. What is the difference? Well, we actually look at that a little bit later, but the point is that if we want to look at the standard deviation of age and look at the variance of age, we use these SD and VAR functions. And you'll see that actually the functions are the same for this answer 15 and 16, mostly because I'm using combining those functions to illustrate their similarities. And that's what should make this syntax relatively simple. That's why it was written this way, that you can basically take the same function, apply different commands to it. So for example, with this function, we can also find out the mean of age. Actually, all I'd have to do is type the mean. There's the mean. So far we've basically reviewed the meaning of these actual arguments that we have in our Studio and the Mosaic, and we've looked at two measures of central tendency, mean and median, and then we looked at two measures of spread, standard deviation and the variance. And I showed you how to answer those questions using the syntax. I also showed you, by the way, what happens when you encounter a problem and why it's virtuous or better for us to save those analyses for later on. Now, I want us to get to this question of why these are numerical data. Someone had asked this before. I just want to show this to you. Remember we have this view function that we looked at earlier. Now, you can also, and I had looked at this, I think I had shown this to you before by using the drop-down menu. You can do this to look at the variables where you have the variable name followed by a colon, followed by the variable type with some example values. So, for example, we know that age is a numerical value. It's read into R that way. Sometimes R will read in values, by the way, or data variables that we don't want to be read in a particular way. But here we see that, in fact, grades are numerical, sports, and these ranking values are actually numerical. And that's what I want to emphasize here, is I want us to look and explore these grades, sports, looks, and money variables. But you'll see there are other variables here too. So a factor variable is a categorical variable. That's just gender, boy and girl. Grade level is the actual grade in which those students are in. So that's actually numerical too. If we're a school, for instance, the school type or school location, those are actual categories. So if we look at the data frame, we can actually view the data frame by using the view function. And remember, this opens it up as a spreadsheet. And we can look at a lot of these variables, but the point I want to look at is if we look at grades or any of these variables, you can actually see why it is that this is a numerical variable. So if you look at the first observation, here we have a boy who's aged 11. This is, by the way, this is why it's sometimes useful to look at rows. You'll see that he's in an elementary school in a rural location. His goal, well, we don't need to focus on that, but when he is asked to rank about the importance of 4 aspects of popularity, you'll see that he puts grades above sports, and he gives a 3rd place to money and a 4th place to looks. So you know this is numerical because each of these 4 variables is only given a value of 1, 2, 3, or 4 for each student. So here we have a 10-year-old, say go to row 4, we have a 10-year-old girl. She places the most importance on money, followed by grades, followed by sports, then followed by looks. And that's one way to look at these variables. In fact, we had messed around or played around with this before, and I could show you how we could look at this by applying a filter. We could do this by applying a, what I did is I accidentally opened that in a new window. So that's what this little command does. We want to keep it here, just so you can see it. You can actually apply a filter. So I can say, well, what about, say, at Well, you can do a grade level. So for this numerical variable, if you want to truncate the grade level, you can do that. Let's say among girls. And then you want to say, well, if you want to look at, say, just look at, observe some girls, and we just look at this. We can see that, at least in this data frame, we can look at a few examples of girls in their rankings. Here we have a girl who's ranking grades, followed by sports, followed by looks, followed by money. And the main point is that we can subset by categories, by numerical values, by anything really. And we can also, again, and we looked at this last week, we can get a reminder within the console. We can do this through the viewfinder. We can also do this through the console. And we do this by looking at using the names function. And this gives us the values of the names, the names of the variables in the data set. Now this is important because it goes back to this case-sensitive feature of R, which is that if I use these functions that I had typed in earlier, but I did not use a capital A when I type in the variable age, then I'm actually not identifying the correct variable. In fact, we'll try it here. We'll see that with a lowercase variable, it says error in evaluation, expression, environment, enclosed, object age not found. Well, keep in mind when it says object, it's really saying it can't find the variable. Because what we're doing is we're actually telling R, there is a variable, an object, there's something to find here that is called age that is in the data set popular kids. So just keep in mind that your variables have to be case sensitive, and that the names function is useful for identifying variables. Now, someone had asked, what are variables? Remember, variables are the columns in data frames. The observations are the rows. And this is important because I'm going to move us from looking at these columns, which is what we do here when we look at the names function, to looking at rows. And there are two ways to do this. And this lets us look at the data frame in the columns, in the console, as opposed to the view, as opposed to this little spreadsheet that we have here. So if I restart the view option and we see these first few observations, I'm going to show this. I'm going to highlight these first 10 observations, because we're going to see what happens when we apply the head function. And this, I think the default is 10. No, it's fewer than that. Okay. Well, so the head function actually lets us look at those first few rows. And here it looks like it's the first 6. Now keep in mind, remember in a data frame, we define the rows as numbers that are not actually values in the data set. And then with the columns are actual variable labels. Remember, we have the names here. So the names are what we printed out using the names function. And here we see the first 6 rows. And we look at girl 6, for instance. She's at grade level 5. She's at an elementary school. And she ranks as most important her looks. And we can see that, we can see these examples here in the window console, or we can also see them here through the viewfinder. So if we look at the 6th observation, we'll look at this. You have the same data set right there, an elementary school child. So that's a way of looking at rows as opposed to looking at just columns. Now, the way to remember this function is you're just looking at the head of the data set. You're just looking at the first few rows. And that's pretty arbitrarily defined quite often. It's the way that you read in the data, or the way that the data were presented to you. So it just happens to be the case that the first observation was a boy here. We can talk about sorting the data later. Remember, I applied the filter here. Sometimes the data will come sorted, But for instance, what matters here is not the fact that the data were sorted from, say, a meaningful grade level from, say, lowest to highest. If you just type in if you click on the button here, but rather that when you read in the data, I'm going to actually review this data frame, rather that the data happen to be read in a certain way. And that's important just to keep in mind, that there may not always be a purpose here when you look at the head or the tail of a data set. It might not be the highest or lowest values. It just happens to be the way the data are read in. So not the lowest value, but these are the last few observations in the data set. Now I want to draw your attention to this fact, which is that here we have the tail, which means these are the last few observations. Here we have the rows, and we see rows 478 all the way back to 473. Keep in mind, we know that these are the last few rows, because if we look at the data frame and the object window, in the environment window rather, we can see that it tells us that it is a data frame object, with 478 observations, in this case children, with 10 variables. So we already know this to be the case because we can see that this is confirmed by our window here. So it's clear to us that the head and the tail are just simply inverses of each other. The one looks at the last few, the other looks at the middle few. The point is not really that this is that systematic, it's just you're looking at a few data sets here and there. Now, I'm going to really introduce us to this new concept that is going to be much more common as we move through R, which is this idea of the assignment function, this little assignment operator rather, probably the most common and unique aspect of R, and it's why it's an object-oriented environment. And I'm going to show this to you. And I'd say we have about 5 or 10 minutes left just to review on these two functions here. The point is that whenever you assign something to another object, you're creating something new. In this case, we're using the sample function to define the popular kids data set as one with 10 rows that are randomly selected. So we're just basically plucking 10 kids, selecting them randomly from our data set of 478 observations. And the point here is that we're actually going to create a new object with a new name. Look at this, and it's also recognized as the data frame. So now we have 2 objects. You notice that I have 3 here because I have an object that is, the last, it's sort of a remnant of the history of what I have. You probably have 2 here. But the point is that this object is a data frame in this case. And you can see that just when I clicked on that data frame, popular kids 10. Now, if you notice, the way you define files, I talked a lot about, it also applies to defining objects or new data frames. You want to have some sort of logic to it. So here, all I did was I took the name popular kids and appended the number 10, because here we have 10 observations with 11 variables. Why do we have 11 variables? Well, look at this, because when we do the sample function, we have the original identifier, right? And that means that's because that may be different depending on this data frame. So here you actually see the identifier looks like it's the same. But we also want to keep track of the fact that we pulled this with an identifier with a larger data set. That's simply because we want to mess around with this data set even more. We want to change these row names so that they make sense, so they go from 1 to 10. We know how to track each child back to the original source. But the point is that this assignment operator, to the left of the assignment operator, almost without exception, is that to be defined. And you then do this little sort of less than plus a dash, and it's typically a space. And this is, that which is defining. And we're going to say the definition, really, right? So R will sometimes, if you have to highlight some syntax and then put it in quotes. So I think if I just do this, yeah, this will just read it as a, yeah. So you'll see that I have these objects here in this working directory, and that's simply the word definition. Or we're going to say object. And you'll notice that if I define this new, I'm simply adding another object to my workspace. Now what you notice is I defined that which to be defined as the word definition. Now I have the object as the word definition. In fact, you'll see that I can create as many objects as possible. This is one risk that you have with this kind of working space, is that it's a global environment, meaning that when you define these functions in this way, when you define objects in this way, they don't go away unless you tell them to go away. And just keep that in mind when you look at your environment window and see what you're defining. Typically, you're not going to define too many, but the point is that for now, we're going to focus on creating data sets as objects, but almost anything can be an object, text, numbers, whatever. And this is the flexibility of R. But for now, we're going to look at this popular data set, kids data set, and we're going to do another sample size of 25. Now we have a new data frame where we have 25 observations, and we can see this here. It's the same basic thing, only we're creating a new subset. And the point is that here we have that. Here's the name of that data set, and here's what we're doing. And the point is that now we can analyze that new data set as if it's something new, or that object. So we can do, we can summarize the numerical data of these subsets as well. Now, I think that's all I want to go to right here, except that this assignment operator is pretty central when it comes to R. And it's important to recognize that R is defining both data as well as values as in our working environments. In fact, we can even do numbers. So we can do, say, let object A equal 2, and object B, assignment equals 6, and then object C is A plus B. You'll see that I'm going to define these three objects. You'll see that C is 11. Why? Because 4 plus 7 equals 11. So you can actually do a lot of interesting things here with both numbers and with text. Right? So you can do, let's say, I'll show you another aspect of objects. You can do A equals hello, and then B equals, notice I'm saying equals because, and this is why I focus on the equal sign before. Equals in R is as part of an argument or function is different than when you're using an assignment operator where you're taking a bit of text to the right of the assignment operator and then defining it as something else on the left-hand side. So if we take the two string variable, the 2 bits of text, hello world, I think we have to combine or concatenate those. We'll do a little function there. Do we have hello world? Yeah, we have a bit of hello world. It's a character that's 2 bits of string long. But the point is, this is why naming objects is also important. The third lesson, the first lesson is that anything can be an object. The second one is that anything to the left of the object can be defined that way, and that you should use meaningful definitions for those objects. The third lesson is you can override names if you use the same function. If you name the same object with the same name, it'll automatically override that name. So here I define A as hello, or I can define A as a number. You'll see that whatever I do last will be the definition of that object. So again, here, this is why objects are a little bit tricky. And we'll talk more about removing and cleaning up the workspace in later sessions. And in particular, tomorrow we're going to focus on more elaborate analyses that focus on, let's see if we scroll down. I just want to show you graphics, and then as well some of these nested functions like the square root of variance. And if we go all the way down, we're going to do some more analyses on these subsets of analyses. So that's it for now. Thank you very much. And if you have any questions, feel free to always keep in touch. And thanks for listening.